Hello students, I am Parthapratim Das. I am a faculty in physics with NIT Karnataka, Surathkal. Today I am going to discuss the series resonance circuit experiment. The slides are taken from a course offered by University of Florida, United States. And if you want to go to that link and you can just pull out more information about this course. So let me explain the first initial few points regarding this particular experiment. So this experiment's name is called series LCR circuit. It is also called series resonance circuit. So let's come to the circuit diagram first. You have basically three electrical components: R, the resistor, the capacitor, and the inductor. Okay. So the capacitor and inductor are energy storage devices. They can store energy. And you know the expression for the energy stored in a capacitor is half CV squared, and the expression for energy stored in an inductor is half Li squared. Okay. So these three components are connected in series with each other back to back, and finally they are connected to one AC voltage source. Now, how do you, so you know this expression, this figure, if you have alternating magnetic field, that's going to give rise to alternating EMF. Okay, so we take the sinusoidal curve. This is your sine curve, and you can also take the sine squared when you, this is going to be important when you talk about the power unleashed by this LCR circuit. So this is pretty much the end, pretty much the circuit for this experiment. Now, while doing the experiment, what you are going to do is you will change the frequency of the AC signal in the input port, and you will basically record the current that flows in all three components R, L, and C. One thing you should always remember: in a series circuit, the current is same through all the components R, C, and L. So while performing the experiment, you will record the current, okay, as a function of frequency, and this is the kind of trend you will get. So when you will see when the frequency is pretty low, the current is also low. As you increase the frequency, the current will ramp up, reach maximum, and then it will go down. So that's the kind of trend you will see in the curve. That maximum point is called a resonance point, and the frequency at which the current becomes maximum in the circuit is called a resonance frequency, and in this experiment we'll call it omega naught or F naught. Okay, so this is one of the objectives of this experiment. Now we can move to the next slide. So the next slide is the voltage and current in RLC or LCR circuits. It depends on the instructor. Some people call it RLC, some people call it LCR. It means the same. So the AC EMF is expressed as something like this. Okay, so epsilon M or EM is the maximum voltage, and we take a sinusoidal voltage source, that is sine of omega t. Omega is equal to 2 pi f. That's the angular frequency. F is the frequency of the AC signal. Basically, you will change the F, the frequency of the AC signal, and record the current in the circuit. So if E is the voltage, then you can find the electric current. So electric current expression is going to be something like that. So Im is the maximum current, Imax, which is epsilon M over R. R is the resistance of the resistor. Okay, that is the case when you have only R. When you have L and C both, so one thing is very pertinent in this at this point is, if you see, the current is proportional to sine of omega t. The alternating voltage or the EMF is also proportional to sine of omega t. So sine of omega t over there, sine of omega t over there. That means there is no phase difference between the voltage and the current, or between the EMF and the current. But things will change when you basically introduce one L or C. There is going to be some kind of phase difference which is expressed in terms of a phase angle phi. So we'll explain what is phase angle phi, and I max is equal to Em by Z or Z. Z is the impedance, the total impedance for the series LCS circuit. So we'll talk about those things in a minute's time. Now, so so let's take the simplest example. So you have the alternating source, voltage source, and you have only the resistance. So this is the driving voltage is given as this. This is the current. So current is I am sine of omega t. In both cases, you have sine of omega t, sine of omega t. That means the current is in phase with the voltage. The phase angle is 0 in this case. Now let's see what happens when you when you introduce C and L. This is the case for C. So now this is your alternating source. This is the capacitance capacitor. The capacitance is C. So you can do this math. This is very simple. If you have the alternating voltage, you can find the expression for current. That is cos of omega t. That was sine of omega t. So you can express cos of omega t as sine of omega t plus 90 degree. So if you look at the current and the voltage, you will see that the current basically leads the voltage by 90 degree. And any electrical component will have its reactance or impedance or resistance. Similarly, so this capacitance, the capacitor will also have its capacitance and reactance. The reactance offered by the capacitance is called Xc, which is equal to 1 over omega c. This is something you know from your school days. But this point is very important. Current leads the voltage by 90 degree in the case of a capacitor. Similarly, you can do the same math and find the phase difference when you introduce one inductor. Okay, this is also like capacitor. Inductor is also energy storage device. So in this case, the current will lag the voltage by 90 degree. In the former case, the current leads voltage by 90 degree. For the capacitor, for inductor, it lags voltage by 90 degree. So these are very preliminary stuff which you have seen in your school days. Now what I am going to do is I am going to find a general solution for RLC circuit. So we assume that the steady state solution for current is something like this. Okay. So Im is the current amplitude or the maximum current. Phi is the phase angle by which the current lags or leads the driving EMF. So we must determine Im and phi. So that's the objective of these two slides. So plug in the solution, differentiate and integrate for sine of omega t minus phi. So this is your current expression. You can take the differentiation and this is your Q. So and then you substitute. So this is your EMF. Okay. If you remember the series LCS circuit, and this is your EMF or the voltage drop across the inductor L. This is the voltage drop across the resistor, and this is the voltage drop across the capacitor. So if you do the math, finally you will arrive at that expression. This is something very easy. You just plug in, take the values from here and plug in there, and you will arrive at that expression. Let's move ahead. So you can slightly rearrange it, and then you can basically rewrite the same equation as this. Now expand the sine and cosine expression. You will get these two equations. Okay. Now what you do is collect the sine and cosine terms separately. So this is this equation for cosine terms and this is for the sine terms. And if you solve that those two equations for phi, the phase angle, and the Im, the maximum current, you will get this expression. This is something very important for series LCS circuit. Look at this, tan of phi, which is equal to omega L minus 1 over omega C by R. This is equal to XL minus XC over R, and this is your maximum current. Z is the uh, total impedance in the circuit. Now, what is XL, omega L? XL is equal to omega L, that's the inductive reactance. XC is equal to 1 over omega C, that's the capacitive reactance. And this is the total impedance. Z is equal to root over R squared plus XL minus XC whole squared. Now, I am going to ask you a question. Why there is a negative sign in between XL and XC? This is something for you to look at. So now what is reactance? Think of it as a frequency dependent resistance. Normally resistance is a quantity which does not depend on frequency, but think of it as a frequency dependent resistance. So look at, this is the reactance offered by the capacitance. So this is 1 over omega C. Xc, the reactance offered by the capacitor, shrinks when you increase omega. So that means Xc decreases when omega increases. In this case, for the case of inductor, the XL, the reactance offered by the inductor, which is equal to omega L, XL increases when omega increases. So there are differences between XL and XC, and that will help you answer that question, why there is a negative sign between XL and XC in the expression for Z, the total impedance. And in case of resistor, it is independent of omega. Okay, this slide is very important for you to take note of. Now what I can do is, I can basically express the different reactances offered by different branches in the circuit R, L and C, and express it in terms of a phasor diagram. So this is called a phasor diagram. Z is equal to Z is the total impedance in the circuit. This is your 10 phi. You just found out that expression XL minus XC over R. And there is also another. You can basically look at this right angle triangle over there. And there is an angle phi, which is the phase angle. Phi is the phase angle. Phi is phase angle. Okay. So you can also have an expression cos phi, which is equal to R over Z. So this expression is going to be very, very important when it comes to explaining the power of the LCR circuit. You remember this expression, cos phi is equal to R by Z at this point, and we'll come back to that point just in a minute's time. Sorry. Now summary of the circuit elements, impedance and phase angle. Okay, so we know what I am going to show. This slide is very important. It summarizes everything whatever we have discussed so far. This column is the total impedance in the circuit, and this is your phase angle, tan theta. So if you have simple R, you have only the reactance, total reactance is R, and there is no phase difference between the current and the voltage. When you have C, you have XC, which is equal to 1 over C omega, and you have this phase angle, the phase difference. So when you have L, you have XL, which is equal to omega L, and you have that phase angle. So similarly, you can basically have different permutation of combination of the different elements, and you can see the reactance in the circuit as well as the phase angle tan phi. So this is your important resonance. So we have found the expression for the total impedance, which is equal to root over r squared plus xl minus xc whole squared. I am just plugging in the values. At resonance, I told you the total impedance should be minimum, and you can do it only by equating XL to XC. So that is the condition for resonance. So that means omega L is equal to 1 over omega C. So that's the thing that you have found. And I define a new frequency, which is resonance frequency. Okay. That is omega naught, which is equal to 1 over LC. At resonance, the impedance Z, the total impedance Z is minimum and current is maximum. So that's why you get this curve. Okay. So you plot frequency, okay, as a function of current. This is your omega naught or F naught. Okay. Omega is the angular frequency and F is the frequency of the AC signal. Okay. That's where you get resonance. So let's move ahead. This is the curve I max I as a function of f. Okay, so this is for the low frequency regime, and this point is resonance. This is your resonance frequency, and if you increase the frequency, the current will start dropping. This is the kind of trend you will see in the current versus frequency curve. There is also a typical example which you can look at. The next important point is power in AC circuits, and in this case the LCS circuits. We know the instantaneous power emitted by circuit is equal to P. P is equal to I squared times R. So you can basically have this expression, and more useful to calculate the power averaged over a cycle, and we'll use this bracket. So when you take the average of this quantity, you will get half. Okay, now I want to get rid of that factor half. How do you do it? You define root mean square quantities for current and voltage or EMF. So this is how you define it. These things are going to be useful when you perform the experiment. The root mean IRMS is equal to maximum current over root 2. E RMS is equal to maximum voltage or the amplitude of the voltage signal EM over root 2. And this is the expression for power, the average power in the LCR circuit. Okay. So this expression is very, very important. We'll just come back to it in a minute's time. Now we have just found the power in AC circuits. This is the expression. This is the IRMS. This is the expression for power. I can rewrite it, and then finally I can have the expression for power. The average power is something like this. Look at the right hand side. You have ERMS, IRMS, okay, and then you have cos of phi. Do you remember that I told you that cos phi is going to come back again? So cos phi was R over Z. So this is the new expression for the average power. Now look at this phasor diagram which I showed you earlier as well. So cos phi is the power factor. This cos phi is the power factor. Why power factor? It is basically P average goes as cos phi. Okay. So to maximize the power in the circuit, okay, so what you have to do is you have to make phi close to 0 because cos 0 is equal to 1. So you can make phi is equal to 0. How? You can just, this XL minus XC must go to 0. That means XL is equal to XC. What is that condition? That is the condition for resonance. So that's why at resonance, phi must go to 0, and that will happen only when the reactances of XL and XC will become opposite to each other or will oppose each other. So the maximum power delivered to load happens at the resonance. For example, too much inductance XL can be cancelled by increasing the XC. Okay, so this is something you can see in the resonance curve. So ultimately, take home message is this cos phi term is very, very important. It is linked to the average power, and power is going to be maximum when cos phi will be maximum, and cos phi will be maximum only when the z becomes minimum, and z becomes you can make z minimum only by putting xl minus xc is equal to 0 or xl is equal to xc, which is the condition for resonance. So let's move to the next one. This power versus frequency and resonance. You can just have a look through that expression. This is the expression for finding out the resonance frequency, which is also there in the handout. Okay, so this marks the end of the underlying theory. Now we will start performing the experiment and then plot the graph. Finally, I am going to talk about the quality factor. So what is the quality factor? Let me explain a bit of this quality factor. Quality factor. It is also called Q factor. How do you define the Q factor? Q factor is defined as the ratio. The Q is equal to, this is a ratio between two quantities. It is a ratio of energy or power stored in resonance divided by energy or power dissipated at resonance. Okay, so that's the expression. Now you can perform some mathematical steps, and then finally for the case of LCS circuit, you can find the expression for Q is F naught divided by F2 minus F1. Now what is F2 and F1? So let me explain those two quantities. In the resonance curve, uh, so the frequency was very, very low. It increases, reaches maximum, and then becomes. So this is your resonance point. So along x-axis you put F, along y-axis you put I, the current in the LCR circuit. Okay, so now I explained the theory. So this is your I max. So you can say this is your I max. You will have two more quantities. Now you take the current at which the frequency at which there are two frequencies F1 and F2 at which the current becomes I max over root 2. Now why it is I max over root 2? I have already explained in the theory. This is mostly connected to the power. Okay, so you just look at the expression for power. You will find out why I basically come to I max over root 2. This is nothing but the RMS value of the current. Now F1 and F2 are the two quantities, two frequencies at which the current becomes I max over root 2. Now if you look at this expression for quality factor Q is equal to F naught divided by F2 minus F1, and this is also frequency, this is also frequency. So ultimately quality factor does not have any unit, no unit. Okay, this is something very, very important for you to remember. Okay, there is no unit for quality factor. Okay, so if you one thing you should remember for getting ideally what should you get? Should you get high quality factor, low quality factor? The answer is the first one. So the quality factor ideally should be much greater than unity. What does that mean? Your circuit, this means your circuit is under damped. If your quality factor is much lesser than unity, it is your circuit is severely damped. Okay. So now what is damping? Damping comes, if you remember in mechanics, damping comes in the case of simple harmonic oscillator. This circuit is also kind of a simple harmonic oscillator. The only difference is what it, in this case, only the electrical energy oscillates. In the case of mechanics, it is the mechanical energy that oscillates. Okay. In the case of mechanics, it is the friction which is basically responsible for damping. In this case, it is the reactances or the impedance, okay, or the resistance in the circuit which is responsible for damping. So ideally what you want is, you want very high quality factor. You want the power dissipation very, very low, and you also want the energy stored in the resonance very, very high. So that's why Q must be much, much higher than unity. That is all. You will do the experiment in real sense. So you have seen this document. That was the handout that we have given to you already. So this is called, this experiment's name is series resonance. So you'll have three electrical components: resistor, capacitor, and an inductor in series with each other. So that's why we call it series resonance circuit. So you have seen in that document that you have to find out certain parameters which are listed over there. Is something I will not explain again. So this is the theory, underlying theory, and this is the circuit. Okay, so let me take you to the real experimental setup now. So this is how the experimental, can you zoom it out? This is the real experimental setup which you will work on. Okay, there are two boxes. This is box 1, this is box 2. Okay, in the box 1 you have the real circuit. Okay, so can you bring it closer? So there are three components, as I told you before. So these components, the first one is inductor, this is your capacitor, and then you have a resistor. All three of them are in series with each other. This is the electrical circuit that you have to make. So there are choices in these three electrical components. There are choices, several choices. So I will explain one by one. Let's come to the capacitor first. The capacitor is in between the two others. Okay, this is capacitor. You have three choices. We'll pick just one. Okay, that is 0.01 microfarad. Okay, and connect that capacitor to this one. So you don't have the electrical components right underneath here. You have somewhere there. We'll pick one by one. Okay, so that capacitor is gone. Now we'll come to the inductor. So inductor is unknown. We'll pick, there are two inductors, inductor 1, inductor 2, L1 and L2. So we'll pick L1. Okay, so that's your unknown inductor. You don't know the inductance of that inductor. Okay, and then we'll pick these two leads and then we'll put it there over these two things. Okay, two leads. Finally you have the resistor. Okay, the resistor, there are several values for resistance. So we'll pick the 750 ohm. Okay, so it's exactly written in the procedure, the way it's written in the procedure. So this is your resistor. So you have three components, three electrical components in series with each other: inductor, capacitor, and a resistor. So that constitutes your series LCS circuit. So this part is kind of off because that is your parallel LCS circuit, which we are not going to work out. Okay, so now there are two ports. You can say this is your input port, that is kind of your output port. Okay, so the input port, you will connect these two red wires to the frequency generator. Okay, so what does it do? It basically generates AC signal of different frequencies. Okay, so if you look at this box 2, I call it box 2, the name is frequency generator. You have several knobs, 1, 2 and 3. The first one, if you look at, this is your set amplitude. So that means you have to set the amplitude at the maximum before you start doing the experiment. That means the AC signal that comes out of these two leads
will have maximum amplitude. So that's the meaning. You set it at the maximum. That's how you do it. Okay. The second one is for changing the frequency. The third one is the scale. Is the scale of the frequency. So normally we'll put the scale at multiplied by 1 kilohertz. Okay. That means this LED panel, the digital panel, whatever number you see, you have to multiply this number by 1 kilohertz. Right now you are seeing 1.0. That means the frequency of the AC signal that comes out of these two leads is 1.0 multiplied by 1 kilohertz. That means 1 kilohertz that is the frequency of your AC signal. Now with this third knob, you can change the frequency. You can see the frequency is changing. So what we are going to do is we will record the current. We will change the frequency, and as a function of that, we will record the current that flows in the series LCR circuit. So that's the meaning of the entire thing. Now I think this part is pretty much done. So if this circuitry is not that difficult, once you go through it, you will be able to understand it pretty quickly. Now what I am going to do is I will change the frequency of the AC signal that you will put in that input terminal, and I will try to record the current through a milliammeter. You have a milliammeter there. This whatever you see in this panel, that's the current in milliamp. Current in milliamp. Okay. Change the frequency, record the current, and then you plot it, and then you perform some mathematical steps, and then finally you will able to find the answers of all 4 or 5 parameters that you want to find out. Okay. So now let me change the frequency. So you can also see if you have seen in the handout, the PDF file that we have given you, you will see the trend for low frequency. The current is also low. As you increase the frequency gradually, the current is going to go up and will reach maximum for certain frequency. We call that resonance frequency. I explained that what is resonance frequency in the earlier part of the video. And once it reaches maximum, after that the current will start dropping. Okay. So current will start increasing, reach the maximum, and will start dropping. So you will get the trend. So if you plot along y-axis the current, x-axis the frequency. So as you increase the frequency, the current will ramp up, reach maximum, and then it will come down. So exactly the way it was shown in the PDF file. Okay. So let me explain now. What I will do is I will, as part of the demonstration, I will show you few data points, and then finally I will give you a data sheet. I will also plot it in a graph sheet. You can also do that. And then finally I will show you how the calculation is done to find out those parameters. Okay. So let me change the frequency. So what I will do is I will touch that knob, I will change the frequency, and I will record the current. Okay. So we have given you some specific value of the frequency, so you have to put only those values. But right now I am just going to show you the trend of current, how the current changes with the frequency. Okay. Let's change the frequency. It was 1.1, it's 1.2. You can see the current is also changing. It's ramping up. Okay. It's ramping up. The frequency is increasing, current is also ramping up. Frequency is changing, it is also ramping up. Okay. So 2.4, current is 1.83. Okay. 2.8, current is 2.27. 2.9, current is 2.89. So that way it will go on increasing. Now slowly it's coming to the peak. So you have to go really slow. Okay. This is 5.8, 6, the current has become 6. It is increasing. Now increasing, it is decreasing. Have you seen that? It was just before that, it was 7, and now it has become 6. The current becomes 6.6 million. So now the current has, frequency is increasing, but current has reached maximum, and now current has started decreasing. Okay, so increase, keep on going, keep on changing the frequency, increase the frequency, record the current is ramping down, ramping down, ramping down, ramping down. So ultimately you will see the trend something like this. Okay, so this is so now I will give you the data sheet, and from there you can plot the current as a function of frequency. So this is the observation. So these are data points. So what I will do is, you are going to record frequency as a function of current. Okay, so if you increase the frequency, so you can see 1.0, 1.2, 1.4, so on and so forth. This is in the unit of kilohertz. So current is also increasing. Okay, frequency increases, current also increases. So for frequency 5.6 kilohertz, you can see the current reaches maximum. So this is your I max. And after that, the current will start dropping or decreasing. Okay. So what you have seen is, if you increase the frequency from lower values, the current through the LCR circuit increases. Then at particular point, for a particular value of frequency, it reaches maximum, the current become maximum, and then it starts decreasing. Okay, so the frequency at which the current reaches maximum is called the resonance frequency. So in this case, 5.6 kilohertz is the resonance frequency. We call it F naught, 5.6 kilohertz. Okay, now we are going to plot the frequency versus current over here. Let me show it there. Okay, so if you can see this one, this graph, let me zoom it in. So what I'm going to plot is, this is your frequency, this is your frequency F, and this is along this is your current in the unit of milliamp, frequency in the unit of kilohertz. Okay, so you can see the trend. For lower frequency, the current is low. As you increase the frequency, current increases, reaches maximum at that point. Reaches maximum at that point. That is your resonance frequency. Okay, this is exactly your F naught, and then current will start decreasing. So current increases and then current decreases, and in between you get the maximum current. That point at which the current reaches maximum is called resonance frequency. There are two other frequencies, F1 and F2. So this is your F1, this is your F2. So F1 and F2 are defined as the frequency at which the current becomes I max over root 2. Okay, so at that particular point, the current becomes I max. This is your I max by root 2. Okay, you know the I max value. This is your I max. Okay. So now if you take the difference between F1 and F2, that's going to give you the bandwidth of that LCR circuit. So this is pretty much the graph, and this is your scale of the graph. Okay, let me explain. So I have explained three things: F naught, F1, and F2. Okay, so F naught is the resonance frequency, F1 and F2 are the frequencies at which the current becomes I max over root 2. Okay. Now we'll have to perform some calculation. So let's do that.
to find the certain parameters. So let me, you have to find 5 parameters. You have to find 5 parameters, and those parameters, the first one is the resonance frequency. Okay, so the resonance frequency is 5.6 kilohertz. Okay, so let me use a different color. So the first one is resonance frequency, 5.6 kilohertz. That's what it is. Okay, the next one is you have to find the unknown inductance of the unknown inductor. And you know, you have the expression that is L is equal to 4 pi squared F naught squared C. You know the value of C. So once you plug in the value, so you will get roughly around 0.08 kilohertz. So sorry, it is Henry. It is not kilohertz. It is Henry. You can also convert it to millihenry. That is the unknown inductance value is 80 millihenry. Then the third one is your bandwidth. Bandwidth is equal to F2 minus F1. That's the modulus, and you can take the difference between the two. Roughly, it is going to give you 5.55 kilohertz. That's the third quantity. You have 2 more quantities. So 1, 2, 3. Yeah, one more quantity. That's your quality factor. Quality factor is defined as F0, F2 minus F1. So that is your. So if you plug in the values, it's going to give you 2.19. So these are the values that you have found out over there. The experiment is done. Okay, so that's it. Bye.